Greetings to all and welcome to this lecture. We are in module 12, small signal modeling, lecture number 1, a low frequency small signal model part 3. In this lecture, we will see how to extract the small signal parameters what we have defined as the transconductance, the source to drain conductance, the body transconductance, etc. in weak inversion, moderate inversion, and how to find in all region model. These are the learning outcomes of this lecture, which helps you to understand the small signal parameter extraction under weak inversion regime of operation. We will also see how these transconductance or source to drain conductance are interrelated with each other. Let us do a quick recap. In the previous lecture, we extracted the parameters like GSD, GM and GMB under strong inversion region of operation. We said that GM can be given by simple equations W by L mu into C ox dash into VDS in non-saturation region, and in saturation region it is given by W by L mu into C ox dash into VDS dash, where VDS dash is nothing but VGS minus VT divided by alpha. We said that the transconductance is not dependent on VGS in non-saturation region, whereas it is dependent on VGS in saturation region, right? We have also said that how we can interrelate the transconductance to body transconductance or transconductance with GSD. We said that GMB by GM can be represented as gamma divided by 2 times of square root of phi naught plus VSB, which is nothing but dVt divided by dVSB, which is nothing but n minus 1, right, where n is the slope factor given by Cb dash by Cox dash, and hence based on the different permittivity and the oxide thickness or the thickness of the depletion region, we define the control of the gate or the body in the channel. We define GSD by GM also, where we said that how my output conductance is related with the transconductance in terms of Dibble or CLM. We said that to calculate GSD, we cannot simply use the simplified model of current, which is IDS is equals to W by L into mu into Cox dash into VGS minus VT into VDS minus alpha into VDS square divided by 2, because when you are going to calculate the derivative of this current equation, then the error will increase, and hence you need to include the correction factors or the second order effects in terms of CLM, channel length modulation, and in terms of Dibble, velocity saturation, etc. We plotted the conductance or transconductance parameter with respect to VDS. We said that when the device entered into saturation region, then GSD goes approximately 0, and this transition from saturation to non-saturation or non-saturation to saturation will be smooth. At point VDS is equals to VDS dash, GM is approximately equal to GSD when measured at VDS is equals to 0 for alpha is equals to 1. That is what we have discussed for strong region of operation. Whereas we have also said that the extraction of these parameters strongly depend upon the region of operation, meaning if we are interested in to calculate these parameters in weak inversion region of operation, then we cannot use the same expression what we have calculated earlier. So let us see how these parameters can be extracted in weak inversion region of operation. We know that in weak region of operation, the current IDS can be given as W by L into mu into some Im dash, which is constant, into 1 minus e to the power of minus VDS divided by phi t into exponential of VGS minus VT divided by n times of phi t. This expression what we have already derived in our previous lecture when we were discussing about the weak inversion region of operation. So as you are interested in transconductance, GM is equals to delta IDS divided by delta VGS, we can simply consider these all are constant. So this W by L into mu into Im dash into 1 minus e to the power of minus Vds divided by phi t, and if you differentiate this, you will get e to the power of Vgs minus Vt divided by n into phi t into 1 over n phi t. This again can be replaced as Id divided by n into phi t. So the transconductance in the weak inversion is dependent on current, or in general we can define the ratio of transconductance with respect to current is constant. So in weak inversion, or how can you define the weak inversion? When Gm by Id is constant. This is defined as weak inversion. Strictly speaking, this expression in a simpler form is coming because we have considered that the current is exponentially dependent on Vgs. However, when you include much more second order effects, this is not exactly exponential, and hence you have to solve complex equation. But for the sake of simplicity, we are considering this equation only, and then we are getting Gm is equals to Id divided by n into phi t. So if the temperature is known, if n is known, I can simply calculate Gm by Id for weak inversion. This is similar as BJT. If I consider a bipolar junction transistor, this is base current, this is collector current, and if I apply the base to emitter voltage, then I can write the equation of current as IC0 e to the power of VBE divided by phi t, where the conductance or transconductance as delta IC divided by delta VBE is nothing but IC divided by phi t, or if I calculate the ratio of Gm by IC, which is nothing but 1 over phi t, right. So you can see the transconductance or Gm by IC of BJT is always greater than Gm by Id because of this factor n here, right, which is a body factor or a slope factor given by 1 plus gamma divided by 2 times of square root of phi naught plus VSB, right. So this is MOSFET. The limit of Gm by IC of 1 by phi t is defined as Boltzmann limit. So accordingly, we can find out what is the ratio of Gm by Id or Gm by IC in weak inversion region of operation, right. Now let's calculate the substrate transconductance, which is nothing but GMB defined as delta IDS divided by delta VBS. Now again you see the equation of current IDS as W by L into mu into Im dash into e to the power of Vgs minus Vt divided by n times of phi t 1 minus e to the power of minus Vds divided by phi t. Here the threshold voltage is coming in the equation, which is dependent on source to body voltage, right, VSB, as Vt is equals to what? Vt naught plus gamma times of square root of phi naught plus VSB minus square root of phi naught. So we can not simply differentiate with respect to VBS. Instead, we need to rewrite this equation as delta IDS divided by delta Vt into delta Vt divided by delta VBS. Again, this is VBS, this is VSB. So when you differentiate it, you will come up with -1. Now, if I differentiate this equation with respect to Vt, I will get the same equation as IDS divided by n into phi t, and because we are differentiating with respect to minus Vt, you will get a minus term, into when you differentiate this with respect to VBS, you will get gamma divided by 2 times of square root of phi naught plus VSB, and as I said that you are differentiating with respect to VBS, so you will get what? -1. So this minus and minus plus, you will left with GMB is equals to IDS divided by n into phi t into gamma divided by 2 times of square root of phi naught plus VSB. This factor is nothing but what? N minus 1. So here you can define GMB is equals to n minus 1 by n into IDS divided by phi t. We have just derived that IDS by n phi t is what? GM. So GMB divided by GM is nothing but n minus 1. This is the same expression what we have obtained when we were discussing about strong inversion, right? So what we said there as GMB is equals to BG times of GM, where BG was given as gamma divided by square root of phi naught plus VSB plus some k 1 minus eta into VDS dash. And we said that when you consider VG or VG and VDS very small, then this BG is nothing but gamma divided by 2 times of square root of phi naught plus VSB, which is nothing but n minus 1. So here again we can relate the controllability of gate and the body on the channel, which means if we define as n minus 1, which is nothing but n is given by 1 plus Cb divided by Cox, we can define GMB by GM ratio in terms of permittivities and the oxide and the depletion thickness, which defines the controllability of gate or the body in the channel. In a similar way, we can find out GSD, which is defined as delta IDS divided by delta VDS. Now again you go back in this equation, differentiate with respect to VDS, you will get GSD is equals to W divided by L into mu into Im dash into e to the power of VGS minus VT divided by n into phi t into this minus and minus plus, so e to the power of minus VDS divided by phi t, correct. Now this term can be replaced as what? IDS divided by this term. So GSD can be written as IDS divided by 1 minus e to the power of minus VDS divided by phi t into e to the power of minus VDS divided by phi t divided by phi t. Here if you differentiate it, you will get with 1 over phi t. That is what we are getting here. So we are taking the same current equation and we are differentiating with respect to VDS, and we are ended up with this GSD. However, as we have seen in our strong inversion case, that we have to include the second order effect, because the error while calculating the differentiation of the current will be more, and hence we need to incorporate the Dibble, right? We know that when we talk about Dibble, the threshold voltage is actually changed, right? So VT naught minus lambda into VDS. Because of the applied drain voltage, the threshold voltage is reduces, and hence this VT here is now replaced by VT naught minus lambda into VDS. When you again differentiate it, you will get the same expression, GSD is equals to IDS dash. Now there will be a term lambda divided by n phi t comes into picture. So you will get lambda divided by n into phi t when you differentiate it, considering the VDS is very large, or VDS is larger than 5 times of phi t, right? If VDS is large, then this parameter or this term will go away, and hence you will be left with n times of phi t divided by this. So GSD can be written as IDS dash divided by VAW, where VAW is nothing but n into phi t divided by lambda, and lambda is nothing but exponential of minus of this parameter. Likewise, if you solve all this, you will get VAW is equals to n into phi t into e to the power of positive of this parameter. Again you see the ratio of GSD by GM depends on the permittivity of the material as well as the channel length, right? So if the channel length is reduces, the Dibble effect will be more, and hence the impact of or the control of the drain side will be more in the channel. That is what this parameter reflects. Now if we talk about the moderate inversion, as we have seen in our previous example, the calculation of the current in moderate inversion is difficult. We generally talk about the weak inversion and the strong inversion, because the charge and the voltage are not following a prescribed rule in the moderate inversion. Similarly, if we plot here about the small signal parameters as GSD or GM, right, or GM or GM by ID, then we see that GM by ID is constant in weak inversion, whereas GM is constant in strong inversion. So if we take this axis as VGS, this is weak inversion, this is moderate inversion, this is strong inversion. In strong inversion, my GM is constant, whereas GM by ID is almost constant in weak inversion. So that is the specification to identify the region of operation. Whereas if you see the moderate inversion, neither GM by ID nor GM is constant or following a prescribed rule, right? That is what we need to go for a modeling precisely while defining this region of operation, that is moderate inversion, right? Here we have defined GM by ID with a normalized value of GM by IDF max. Similarly, GM with a normalized value of GM max. It is clear that in weak inversion GM is negligible, whereas in saturation it is constant, right? Similarly, GM by ID is constant in this. We can consider from a basic physics, like in weak inversion what happens is when you change the voltage, right, this change in voltage changes the barrier height and added the charges here. It means what? The slope is constantly changes per change in the current, right, because the small change in the voltage in the weak inversion changes the barrier height and adds the carrier, which means GM by ID is constant. Whereas in strong inversion, the change in the voltage adds more, a constant amount of charge into it, right? That is what GM is equals to delta ID divided by delta VGS. So change in voltage in the saturation added a constant amount of charge and hence the constant amount of current. That is what GM is constant in strong inversion, right? Now let's define this extraction of the parameters in all reason model. In all reason model, we know the current expression can be given by this, right? So we are not using a simplified model as we have used in weak inversion or strong inversion. We are just using a basic equation which is applicable in all reason, right? So all reason of operation, the current can be given by W by L into mu into integration of VSB to VDB minus QI dash into dVCB. These parameters are well defined in our previous lecture, where VSB is the voltage measured near the source and VDB is the voltage measured here. Correspondingly, the surface potential is psi S0 and psi SL. Correspondingly, the inversion charge is QI dash 0 and QI dash L. In between, we considered that this is my channel length, right, and VCB is the voltage which varies from source to drain. That is what we have integrated it, right. So in addition, we know that if we change the reference from body reference to source reference, we can simply define VDB is equals to VDS plus VSB and VGB is equals to VGS plus VSB. So this equation can be defined as W by L mu integration of VSB to VDS plus VSB minus of QI dash dVCB is equals to IDS. Now we are interested in calculating, that will give me the source to drain conductance, which is nothing but delta IDS divided by delta VDS. So to simplify this, we can use the Leibniz rule of integration, which says that if a function fx is integrated between ax to bx and function is having a variable of t and x, then we can simply find the derivative of this function. Conditions like the lower limit is constant. So here in our case also the lower limit is constant and the function is not the function of x, So if we do this, fx is equals to 0 to x ft dt, I can simply find the derivative of fx as fx. So simply, if I am calculating the derivative of IDS with respect to VDS, will give me what? W by L into mu is constant, minus of Qi dash measured at VDS plus VSB, right? That is the meaning of this Leibniz rule. This function as a function of or at VDS plus VSB, right? So this is GSD. Now suppose if I am interested in GSS, then GSS is equals to minus of delta IDS divided by delta of VBS, right? So if you use a lower limit, there will be a negative sign comes in, and that negative sign is this negative sign will get cancelled. Sorry, this is VSB, right? So this negative sign will get cancelled, and you can define W by L into mu Qi dash with a negative sign measured at VSP. This is GSS. Now we have a well defined notations. What is the inversion charge measured at VDS plus VSB? Or I can simply say what is the inversion charge measured at VDS plus VSB is nothing but what? VDB. So this is defined as QIL dash here. Similarly, the inversion charge measured at VSB near the source is defined as QI dash 0. So finally, we'll ended up the equation of GSD and GSS using all reason model, right? So finally, we ended up the expression of GSD and GSS, right? So we can simply rewrite GSD is equals to mu into W divided by L into minus of QI dash. We know that QI dash is can be written as minus of COX dash into VGB minus V flat band voltage minus psi s minus gamma root psi s. As we are talking about QIL, it will be minus COX dash into VGB minus V flat band voltage minus psi SL minus gamma root psi SL. So this minus and that minus will be plus. You will left with COX dash into VGB minus V flat band voltage minus psi SL minus gamma root psi SL. So ultimately, we represented the source to drain conductance in terms of surface potential. Let's do a quick check. Using the all reason model, we will see what will happen when we consider the saturation case. So in the all reason inversion model, the current is given by this, where IDS is equals to W by L into QI dash square minus QIL dash square divided by 2 into alpha into COX dash plus phi t into QIL dash minus QI dash. So now we'll see, we'll derive delta IDS divided by delta VSB with a negative sign will give me what? GSS. Considering a saturation region of operation, we said that QIL will be 0 in saturation, right? So this equation can be rewritten as W by L into mu into 1 over 2 into alpha into COX dash QI 0 dash square minus phi t into W by L into mu into QI dash 0 is equals to IDS. Let's solve for QI dash. So QI dash 0 square minus 2 alpha COX dash, because if you divide by this factor will get cancelled, into phi t into QI dash 0 minus 2 alpha COX dash divided by W by L into mu into IDS is equals to 0. Let us consider this as A. So you left with qi dash 0 square minus 2 into alpha into cox dash into phi t into qi dash 0 minus a is equals to 0. You can solve this quadratic equation as is equals to 2 into alpha into cox dash into phi t plus or minus square root of 4 alpha square cox dash square into phi t square minus and minus plus, this is 2 into alpha, so it is 8 into a divided by 2. So you will left with alpha into cox dash into phi t, take out, you will left with 1. Now whether we will take positive sign or negative sign, we have to take negative sign because the inversion charge will be negative. So qi dash 0 negative, as we have taken 2 into 2 to get cancelled and you have taken alpha into cox dash as common, you left with 1 plus a 2 divided by alpha square cox dash square into phi t square. Okay. Now this can be rewritten as qi dash 0 is equals to alpha into cox dash into phi t, factorize it as 1 plus square root of 1 plus 2a by alpha square cox dash square into phi t square, and in the numerator you will get 1 minus 1 minus 2a by alpha square into cox square into phi t square. This get cancelled, this get cancelled, you will get minus 2a by alpha into cox dash into phi t divided by 1 plus square root of 1 plus 2a by alpha square cox dash square into phi t square. This is what is qi dash 0. Now to calculate GSS, we need to take W by L into mu into minus of qi dash 0. So this minus and that minus will get cancelled. But first let calculate separately as what is 2a by alpha into cox dash into phi t. So 2a, we have defined a here, into 2 alpha cox dash into IDS divided by W by L into mu into here alpha cox dash into phi t. So alpha cox dash cancel, you will left with 4 times of IDS divided by W by L into mu into phi t. Now define 2a divided by alpha square cox dash square into phi t square as 2 into alpha cox dash into IDS divided by W by L into mu into alpha square cox dash square into phi t square. 1 alpha 1 cox dash get cancelled, you will left with 2 into 2 4. 4 IDS divided by some W by L into mu into alpha into cox dash into phi t square, right. So we define a characteristic current which is defined as Iz, right, and this is nothing but W by L into mu into cox dash into 2n, where alpha is replaced by n phi t square. So if you replace this, you will ended up this equation as GSS is equals to IDS divided by phi t into 2 divided by 1 plus square root of 4 times of IDS divided by Iz plus 1. Here it is important to note that the ratio of IDS by Iz is very important to define GSS, right. We will see that if we plot the GSS by ID, then there will be a parameter IDS by Iz will comes into picture. So let's, if we do further simplification, we can simply get GM as GSS by N, and if we talk about the saturation region of case, then GSD is equals to 0. almost negligible. So we know that GSS is equals to GM plus GMB plus GSD. In saturation this goes 0, so GSS is equals to GM plus GMB. Now GM is GSS by N, so GMB is nothing but GSS into 1 minus 1 by N, or GSS into N minus 1 by N. Again this tells us how my GMB and GSS are interrelated. So to find out the interrelation between GSS and GM, we plotted in a same scale. This is GSS by ID into phi t, and this is GM by IDS into N phi t for weak and strong inversion, where this point is actually the cutoff point, which says that in this, if IDS by IZ is less than 1 or IDS is less than IZ, you are in weak inversion. So in weak inversion this is the case, and in the strong inversion this is the case, which actually defines that if we know N, if we know a particular temperature, then we can find out Iz. Based on IDS by Iz, we can define whether we are in weak inversion of operation or strong region of operation based on these parameter values, right? Further, we plotted log GM with respect to log IDS, right? As we have discussed that GM is nothing but IDS divided by N times of phi t, where 1 over phi t is the Boltzmann limit, and always the MOSFET GM is less than the BJT. So this dotted line shows for MOSFET and this shows for BJT. Now these few lines are with varying W by L ratio. So this region of operation is weak inversion and this region of operation is strong inversion, where we have seen that my GM changes with respect to W by L in strong inversion. So for analog design perspective, it is good to have a different GM based on different W by L, whereas it will not change in weak region of weak inversion region. We have also plotted few of the characteristics with respect to VGS, which shows that how my GM, GMB and GSD varies with respect to VGS. When VGS is very small, you are in weak inversion, right? Then you are in saturation and then you entered in non-saturation region. In non-saturation region, GSD will be there, whereas in saturation region, GSD is negligible. So this graphs look like this. However, in saturation region, GM is dominating and then it gets constant in non-saturation. So what happens is GMB is less than GM, which shows that the gate control is more than the body control. Similarly, we have also plotted different parameter, different small signal parameters like GBD, GMX, GGD, GGS with respect to VG, which shows different region of operations like weak inversion, strong inversion, and so, right? Here, the second order effect shows this kind of trend, means if we include the mobility effect because of the gate field, then it shows that GM is decreasing when VGS is increasing beyond a value, right? So this kind of trend will be observed because of the second order effect, what we need to include for the precise calculation of these parameters. So let me summarize this lecture. In this lecture, we have discussed about the extraction of the small signal transconductance and conductance parameters like GMB, GM, GSS, GSD, etc. in weak inversion. We have also said that GM by ID is constant in weak inversion and GM is constant in strong inversion. We need to precisely model such that we can simply define the moderate inversion region of operation. We also said that if we calculate GM by ID, then 1 over n times of phi t will be obtained, which is similar as BJT. However, because of this n, the GM of MOSFET will always be lesser than the BJT. So we will stop here for today. Until then, take care.